All right, we're ready to get started. As you can see, I don't have my microphone with you, so if you cannot hear me, please come a little bit forward. So, I know that you went over nomenclature last Friday, but today I want to finish up on the bonding theory of, well, use both quantum mechanical and also classical mechanics. And we'll see like how these bonding theory meet with each other and how to best use all these bonding theory in organic chemistry to predict selectivity. So today you won't feel like it's not like too organic. We're not doing arrow pushing too much, but today will give you a foundation of understanding stability of reactive intermediate. All right, so this is our last lecture on bonding theory of organic molecules. So before we get started, I want to make sure we're on the same page. So I'll do a very quick summary on what we already covered. So if any of these terms you feel like it's totally unfamiliar with you, I highly recommend you go back to the textbook or review our lecture note a little bit more. So getting started, atomic orbitals. So let's, for example, what are the valence atomic orbitals of carbon? So that is our 2s atomic orbital and our p atomic orbital. So my s atomic orbital will have a spherical shape. Well, when we say it is atomic orbital, these are hydrogenic or one electron wave functions. All right, so these are quantum mechanical wave functions or mathematical functions you can actually solve. And we have our 3p atomic orbitals. That is, if we're using the Cartesian coordinate, x, y, and z, we have 3 of them aligned on each axis. Now this one is coming in and out from the screen. All right, so these are atomic orbitals. And then when we are making chemical bonds, these atomic orbitals will interact with each other to form a chemical bond from the quantum mechanical point of view. So there are 2 different types of interactions that can take place. One, in the LCAO-MO, or the linear combination of atomic orbitals. We're saying we're making molecular orbitals by linear combination of these atomic orbitals. Or in plain English, we're adding or subtracting the atomic orbitals from one another. Right, so you can imagine a constructive interference or destructive interference of the wave. So we have constructive or destructive. So I'm just going to randomly pick, let's say, my PZ atomic orbital as an example. A constructive interference would mean these lobes will align with each other. Right, so if you imagine this one to be one of my carbon atom, this one is another carbon atom, the overlap of these atomic orbital gives you a bonding molecular orbital. Alternatively, you can also have destructive interference where the lobe does not interfere, does not implant with each other. So we end up with a node in between. So for the constructive interference, we call them bonding MO. And for the destructive interference, we call them anti-bonding MO. So that's the LCAO-MO theory, or linear combination of atomic orbitals. So pros and cons. Good thing about the LCAO-MO is we can use the energy correlation diagram to predict what's the energy of my bonding and anti-bonding MO. So we have an idea about which one of these orbitals is lowering energy. So in this case, the bonding MO will be lowering energy. So it gets filled first. And you can calculate, say, bond order from the from the correlation diagram. The bad thing about the LCAO-MO is that it's predicting the electron density to be delocalized over the entire molecule. So as a matter of fact, it's hard for us to say where exactly are the sigma bonds of the molecule. Alternatively, we have valence bond theory alongside with hybridization. So in valence bond theory, what we're taking is a product of 1 electron atomic orbitals. And since we're only looking at product of singly occupied atomic orbitals, sometimes we need to hybridize the atomic orbitals so we have enough singly occupied atomic orbitals. So for example, in carbon, we end up having 4 sp3 hybridized atomic orbitals, each singly occupied. And that hybridization tells us, okay, our carbon makes 4 single bonds, or potentially make 4 sigma bonds if the center carbon is sp3 hybridized. And the name sp3 tells us this hybridized atomic orbital consists like 1 s atomic orbital and 3 p atomic orbitals mix match with each other. All right. And the good thing about the valence bond theory is it gives us localized molecular orbital. So it tells us where my sigma bond is. The bad thing about valence bond theory is we don't know too much about the energies of these chemical bonds. Right, so pros and cons. LCAO-MO delocalized gives us information about energy. Valence bond theory localized, but no information on energy. And at the same time, we also have resonance and classical bonding theory. So note that resonance and classical bonding theory, they're not technically speaking correct because we need to use quantum mechanics to describe electrons. But if we're treating the electrons as like charged particles, the classical bonding theory gives us a good way to quickly predict what the connectivity of my atoms are. So in the classical bonding theory, we went over Lewis dot diagram, we went over resonance, we also went over the VSEPR, which predicts the shape of the molecule. So all these bonding theory actually works together in organic chemistry. So we will be using terminologies in all 3 of them whenever it comes to be needed. So if any of the things I just talked about, you feel like it's totally unfamiliar with you, it's time for you to review these concepts before we move on. Right. And today we're going to use the allylic system as an example to demonstrate in organic chemistry, how do we use all 3 of them all together to try to understand reactivity in organic chemistry. So let's get started and see if you get a better understanding in bonding in organic chemistry after today's lecture. So the system of interest we're talking about today is allylic systems. So we start from experimental observations. So chemistry is, again, it's a science, right? So chemistry is deeply rooted on experimental observation. We first have experimental observation, and then scientists develop theories to try to generalize that experimental observation and apply it to other kind of situations. So we start from experimental observation, which in this case, we're thinking about the stability of a free radical. So on the left-hand side, that's the way we do arrow pushing. If you remember, the way we draw it this way means like the 2 electrons in that single bond, one goes onto the carbon, the other goes onto the hydrogen. Right? So in this case, we call this hydrogen an allylic hydrogen because it's neighboring to a double bond. And for this process, experimentally, we can measure what is the bond dissociation enthalpy, or how much energy is being released for this reaction, or how much energy released or required for this reaction that we're breaking this carbon-hydrogen bond. All right. So for this allylic hydrogen, the energy required to break this bond is 87 kilocalories per mole. So that's something experimentally measured. In comparison, if we look at the bond dissociation enthalpy for the alkyl examples, like in this case, if we're forming a tertiary carbon radical, the tertiary means we have 3 R group connecting to that carbon, and we're breaking the CH bond here. What we're getting the bond dissociation enthalpy is larger than what we observed with that allylic CH bond. All right, so this formation of the tertiary carbon-centered radical is endothermic by 96.5 kilocalorie per mole. And the trend sort of goes on. The formation of the secondary carbon-centered radical, when we say secondary, we're saying we have two R group surrounding that carbon-centered radical and one hydrogen. And the bond association enthalpy to form the secondary radical is even larger than the tertiary radical. And for the primary, or we have only one methyl group attached to that carbon. For the primary, the energy it takes to break that CH bond is even larger. So in here, we make a distinct observation is, well, the allylic CH bond seems to be much easier to break comparing to like primary, secondary, and tertiary radical, or tertiary CH bond. Or the other way to put it, if we think about what are we looking at, we're talking about the energy, relative energy between your product and reactant. So a smaller difference between your product and your reactant is suggesting my product radical, my allylic radical, is more stable comparing to my tertiary radical than my secondary radical than my primary radical. So from this experimental observation, the question we're trying to answer here is what stabilizes this allylic radical? Yes?
Here is listed, but I don't, what is radical, what is allylic?
I'm getting there. So thank you for that question. So a little bit back on the nomenclature. So radical means a singly unpaired electron. So in this case, if you think about we're breaking this single bond, right? The two electron, one goes onto the carbon, the other goes onto the hydrogen, right? So the result here is we're forming a H dot or a hydrogen atom, and we have a carbon-centered radical. So there's a single unpaired electron. So that's the radical. Allylic is the nomenclature of this specific system. Means that this radical is right next to a double bond. All right. And feel free to interrupt me in the future if I forgot to define a term and then just going too fast. And thank you very much for that. Any other questions before we move on? So this is just experimental observation. Okay, yes?
Does the breaking of bonds considering tertiary, secondary, and primary, does that have to do with the polarity and how, I guess, if there's more pull to the left side, then it'll be, I guess, easier to break?
Well, yes and no. So we will go over haloalkane chapter and talking about the easiness of breaking that bond. But for now, polarity does not come to play because when we're looking at tertiary, secondary, and primary, we're only looking at, well, whether the carbon is attached to a hydrogen or a carbon. Now, hydrogen and carbon have pretty similar electron negativity. So in both cases, polarity doesn't come to play. In all these cases, we're thinking about that bond being pretty unpolar. Yes?
The allylic hydrogen that you mentioned, is that the one at the very top or the one attached to the carbon?
So the one attached to the carbon next to a double bond is considered an allylic hydrogen. All right, so in this case, this molecule have multiple hydrogens on there. So how many allylic hydrogens are there? So all three on this carbon are allylic hydrogens. All right. And let's move on to talk more about allylic radical. And later on, it will come back and makes more sense to you, like why the allylic system is so special. And the whole point for studying the allylic system is because it is special. It has very high stability. This radical itself is very stable. So we're going to look at it in two different perspectives. We'll first look at it from the classical bonding theory and resonance stabilization. And then we'll try to use the quantum bonding theory to answer the question, that is why resonance provides stability of these radicals. All right, so getting started. Let's look at the delocalization of the allylic pi electrons. So again, when we say something as allylic, if it is a radical, we're saying that's a singly occupied electron. In this case, how can we draw the resonance structure of this allylic radical? If we're doing the arrow pushing, well, we can imagine the double bond, the electron in here, pair up with that singly occupied electron to form a new double bond on the right-hand side, and the other one get pushed to the left carbon. So we can write the resonance structure so that my radical is on left carbon instead of the right one. So that's a resonance structure we can write. All right. And to refresh your memory, when we write the resonance structure like this, effectively what we're saying is the reality is an average of the two resonance structures. So sometimes we also draw it like that. And in classical bonding theory, you sort of just come naturally to say, okay, we have resonance and stabilizes my radical. But the question is, why the resonance stabilize our radical? And before we move on, I'm just going to do the same to, instead, on top of radical, the same also applies to like positive charge and negative charge. And these all have different names for it. Like, for example, if we have a positive charge, then this term becomes a carbocation. So it's a positive charge. Yes?
For bonds, how do you know that for the resonance structures, the bonds actually changing from single to double?
It's not I have to know. There's only one way you can push the electrons so that they still have like favored octet if possible. All right, so there's only one way you can push it. Like this double bond get pushed onto the other single bond, and we form a new bond on the right.
Is it not the same thing as the atom just switching back and forth?
Okay, so don't think about it that way. So that's the whole point. Like, don't move your skeleton when drawing the resonance structure. So what we're trying to say here when we're drawing the resonance structures is, yes, you can just rotating things, right? But what if we keep the skeleton unmoved and we're moving the electrons? How many possible ways the electrons can move around that molecule? All right, so keeping the skeleton unchanged and only move the electrons surrounding it. And the same applies, right? The same kind of operation, we can do it with like positive charges. The same idea is we're pushing the bond from left to the right, and we get a pair of resonance structures. So a carbocation now is a positively charged carbon atom, and we call this one an allylic carbocation, because the carbocation is right adjacent to a double bond. So allylic carbocation, allylic radical. And then the third example is an allylic carbanion. So this is a negative charge. So my negative carbanion is, well, pushing it this way. And we end up having a single negative charge on the left. So in all three cases, we can see we can draw resonance structures And, well, when we draw resonance structures like that using classical bonding theory, we always say resonance stabilizes the carbocation, resonance stabilizes the radical, resonance stabilizes the carbanion. So in the next part of my lecture, I'll try to use quantum bonding theory to analyze the same set of allylic system and see what exactly is the bonding look like in these allylic systems. All right, with me so far? So this part is we're just introducing allylic system to be a special system that carbocation, radical, and carbanion are all stabilized. Using classical bonding picture, we're like saying, okay, resonance stabilizes these like radicals, cations, or anions. But now the question is why this resonance stabilizes the radicals, carbocation, and anions. So that is called the delocalization of the allylic pi electrons. Or the other way to put it is now we're trying to use quantum bonding theory, both of them, and try to depict what does the pi electron look like in these allylic systems. So these are things that we just did together, right? You have radical, you have carbocation, you have carbanion. And what we're gonna do together is write out the bonding of these allylic systems. So I'm gonna randomly pick this carbanion as an example, but the same applies to the other two systems as well. So you can try it yourself later on. I'm just gonna draw that on the board for your reference so that you know what I'm talking about. We're looking at CH double bonded to CH2 in resonance with each other. All right. So in the bonding theory, let's get started by constructing the molecular skeleton. And remember, when we were talking about the two bonding theory, you have LCAO-MO, and then you have valence bond theory. Now, valence bond theory is very good in constructing sigma bond because the bonding using valence bond theory are localized. So we want to use the valence bond theory to first identify where are my sigma bonds. So in this case, what do we have? We started by looking at the hybridization of my carbon. So in all my 3 carbons, they are sp2 hybridized. So all 3 of them are sp2 hybridized. With me so far? So for a sp2 hybridized carbon atoms, what do we have? We have 3 sp2 hybridized atomic orbitals that makes sigma bonds. And we have 1 p atomic orbital that is ready to make pi bonds. So in this case, my center carbon will always have 1 singly occupied p orbital, because you can see the partial charge is never centralized on your center carbon. So my center carbon always have only 1 electron in its p atomic orbital. All right. And then for the 2 terminal carbon, if we do the same kind of analysis, we end up getting 2 different kind of energy diagram. So for the neutral terminal carbon, I don't care which one it is, it can be left or right. We have 3 sp2 hybridized atomic orbitals ready to make sigma bonds. We have 1 singly occupied p orbital ready to make pi bonds if the carbon is neutral. And then these makes sigma bonds. And then for the negatively charged carbon, again, I don't know which one of it. One of it is negative, one of it is neutral. We have sp2 making sigma bonds. And then we have a doubly occupied for pi bonds, or lone pairs, if you may. All right, so this is just drawing out what are the hybridized atomic orbitals do I have. And now we're ready to put the puzzles together. So first step, looking at the hybridization of each carbon. And then we're ready to sketch our sigma bonds. So our sp2 atomic orbitals makes sigma bonds. So for sketching the sigma bonds, what do we have? We have a carbon in the middle, and the center carbon have like 3 sp2 hybridized atomic orbitals. And, well, one of them makes a bond with the hydrogen, and the other 2 are making sigma bonds with the other 2 carbons. And the other 2 carbons all have sp2 hybridized. So that's the skeleton of my sigma bonds. All right, so each of the carbon have like 3 sp2 hybridized atomic orbitals to make sigma bond with either hydrogen or its neighboring carbon. So each carbon making 3 bonds, 3 single bonds with its neighbor. So that's our sigma bonds. And now if we think about it, what do we have left? We have 3 p atomic orbitals ready to form pi bonds with each other. All right, so these 3 p atomic orbitals, whether it's occupied with electrons or not, we're ready to make pi bonds with each other. So in this case, we're ready to use our LCAO-MO to come up with a pi correlation diagram using the MO theory, molecular orbital theory. So molecular orbital theory, remember, we're doing constructive versus destructive interference of my atomic orbitals. So in here, we have 3 p atomic orbitals. And when we're putting it onto the skeleton, now this line on the background, those are my skeleton. That means my carbon-carbon single bond, carbon-carbon single bond. And the hydrogen doesn't come to play with my p atomic orbitals because the hydrogen are just bonded with the carbons through the hybridized atomic orbitals. So only the p electron contributes to my pi correlation diagrams. All right, so how many p atomic orbitals do we have? We have 3 for 3 carbon. So consequently, we get 3 molecular orbitals. We start from 3 atomic orbital, we end up with 3 molecular orbitals. So the way we create these molecular orbitals is based on the number of nodes available. So in the all bonding molecular orbital, all 3 of these lobes are in phase with each other. So it's fully delocalized over the entire molecule. There's 0 node plane. So there's no change of sign between your atomic orbitals. And in the middle, we have a non-bonding molecular orbital, meaning like there's 1 node plane on the carbon, and the molecular orbital will change its sign once. And then you have the fully anti-bonding molecular orbital. All right, so when drawing these pi correlation diagram, the steps you want to take is first think about how many molecular orbitals are there. So the number of molecular orbitals equals to the number of atomic orbitals creating these molecular orbitals. That's rule number 1. Rule number 2, after you decided how many of them, you decide how many nodes are there. Like in this case, 0, 1, 2. We always increase the number of nodes with respect to energy. So bonding MO with less number of nodes will have lower energy. Anti-bonding MO with more number of nodes will have higher energy. Side note, what is a node? Like, why do we care about node and position of the node? Now, whenever we say there's a node, we see that's a change of sign of my molecular orbitals, right? So we're flipping the face of the molecular orbitals. And a node plane tells us that is the low electron density region of your molecule. All right. So in this case, when we're looking at carbanion, now we're ready to populate electrons into these pi correlation diagram. So when we're creating these pi correlation diagram, I don't care how many electrons are there. Once we created these pi correlation diagram, we're ready to populate electrons onto the pi correlation diagram. So how many electrons are there for the carbanion? So that goes back to our original analysis. You see, like we have 1 for the center carbon. We have 1 coming from one of the neutral terminal carbon. We have 2 coming from the negatively formal charged terminal carbon. So in total, we have 4 pi electrons we need to populate into our pi correlation diagram. So we do it from bottom up. So it's a matter of, as a result, we end up with 1, 2, 3, 4. All right, so when we're drawing the pi correlation diagram, we start by drawing the pi correlation diagram itself, and then we populate electrons into there. And last step, we're ready to analyze these pi correlation diagram with electrons in them. Like in this case, what do we have? We can identify our highest occupied molecular orbital. And our lowest unoccupied molecular orbital. All right, so in this case, if we're predicting the reactivity of my allylic carbanion, let's do a little bit of mental practice. Is it going to be able to accept more electron, or does it want more electron? Like, where that electron is going to go if we add 1 more electron to the system? It's going to go into the anti-bonding MO, right? And that's unlikely, because whenever we're putting electrons into the anti-bonding MO, we're destabilizing the chemical bond. So that's why carbanion will never want more electron, unless it doesn't have any option. All right, that's rule number 1. Rule number 2, where are my anionic charge looking at this picture? Well, so whenever there is a lobe, it's telling us, well, that's where my orbitals is. That's where my electron densities are. So in this case, what are we predicting? We're predicting that negatively charged to be evenly separated on the terminal carbons of my HOMO. Right, so that's where my electron density gonna be. Or in the summary here, the question is, where is my negative charge? And you take out the shape of the HOMO coming from the orbital analysis, and we can say that, okay, so the negative charge will be delocalized on the terminal carbons. Or electron. All right. And let's see what exactly can we get by applying this kind of analysis into our radical and carbocation. What do we have? So taking one step further, we see that allylic carbocation and allylic radicals are similarly delocalized. So if we're looking at the carbanion, we have a total of 4 electrons we need to put it in. If we're looking at a radical, we have 3 electrons. And if we look at a carbocation, we have only 2 electrons to pop in. And doing the same kind of analysis, now, if we're looking at the carbocation, and thinking about reactivity of the carbocation, first question, what is the HOMO and LUMO of my carbocation? So the HOMO, the highest occupied molecular orbital, is the bottom one, where all the electrons are evenly delocalized over the 3 atoms. The LUMO, or the lowest unoccupied molecular orbital, is the center one, with the 2 dumbbells or 2 orbitals on the terminal carbon. All right. So now the question becomes, now imagine we have a nucleophile attacking this allylic carbocation. Where will that reaction take place? If you have some kind of nucleophile ready to interact with the carbocation, where will that reaction take place? Anyone want to try? So that's going to take place on the terminal carbons, right? Because that's where your vacant LUMO atomic orbital is. And that's when the nucleophile comes, that's where it's going to interact with. All right, and the whole point of resonance stabilization is, well, chemists want to use something that's as simple as resonance structures to best describe the quantum mechanical picture of these bonding. So this is the real way to analyze the bonding using quantum mechanics. But the resonance analysis gives you the same conclusion by drawing 2 different resonance structures like what we did there. All right, so knowing how to draw the resonance is good enough for you to understand most of the mechanism discussion in this lecture. But at the same time, I also want you to know what is actually behind the resonance stabilization. So that's the delocalized pi atomic orbitals. It will come to play later on in your next quarter when you come to talk about aromaticity. It will come to give you a better understanding in what are we talking about when we're saying delocalized pi electrons. And this is the simplistic possible system of delocalized pi electrons. All right. And as a quick summary, for allylic systems, whenever we have allylic radicals, cations, and anions, these are more stable than non-allylic versions. And they're more stable because of the delocalized electrons or positive charge or negative charge. And the partial radical cation or the anion characters will be present on the terminal carbons of these allylic systems. Okay, any questions before we look at an example together? Or you're too confused and don't know what to ask? Okay, yeah.
So are the carbocations the least stable then? If they're the most reactive?
Okay, so the question is, are the carbocation the most reactive? I think before I answer that question, you want to ask yourself, what is reactivity? So when we are in organic chemistry, when we are talking about reactivity, we're always talking about reactivity with respect to another substrate. Right, so in this case, when we're saying carbocation is more or less reactive, we can say carbocation is more reactive when interacting with a nucleophile or an electron donor. Your carbocation is more likely to interact with an electron donor. Alternatively, your carbanion is more likely to interact with an electron acceptor or an electrophilic part. Right? So depending on the other part of your reaction, the reactivity pattern also changes. Yes?
So then is the radical just the most overall reactive? Because
No, you can't compare the reactivity between radical carbocation and carbanion, but you can compare the relative reactivity of an allylic radical versus a non-allylic radical.
Okay. So, sorry, final question. How does this tie back into the bond dissociation energies?
All right, so back to your question, which one of them is more reactive? So this whole point here is we're trying to demonstrate it's easier to homolytic cleavage the allylic carbon-hydrogen bond because we're forming the more stable allylic radical comparing to like tertiary CH bond or secondary CH bond or primary CH bond. All right, so we can compare relative reactivity of the same reactive intermediate like radical or carbanion or carbocation, like allylic more reactive than non-allylic. And let's look at one example together and see like, why do we care? It's like, why are we talking about all these shit in organic chemistry? Let's look at one example here. All right, so the whole point is I don't want you to just remember like selectivity in organic chemistry. That's the only thing I wish like my class is not going. I really hope you can predict selectivity in organic chemistry based on understanding of these reactive intermediates. So this is one example together. So the question here is we have a hydrolysis of allylic chloride that can potentially form two different products. And we're telling you the reaction will proceed via a carbocation intermediate. Well, so a carbocation, again, is some kind of carbon-centered, like carbocation, carbon-centered positive charge. And the question is why the product A and B are formed, but C is not formed. So these are the structures of my A, B, and C. All right. So for this kind of question, without knowing anything about the reaction, how can you predict and rationalize the selectivity of an organic reaction, even if you haven't seen it at all? So that's the power of understanding bonding in organic chemistry. So let's read it together and write it out. What do we know? It says the reaction proceeds via a carbocation intermediate. So this is my reaction. We must form some kind of carbocation intermediate. So how do we form a carbocation intermediate? Well, we're breaking this carbon-chlorine bond. Right, so the electron go to chlorine. We're also telling you we're forming a chlorine minus. So the electron must go from that single allylic carbon-chlorine bond into the chlorine atom. And we end up getting the intermediate, well, to be something like this. I'll do it one more time. So the question reads, the reaction proceeds via a carbocation intermediate. So we ask ourselves, what is a carbocation intermediate? That carbocation intermediate is a carbon-centered positive charge, right? And in this process, looking at only the left part, we know that we're dissociating a chlorine minus to form this carbocation intermediate. So it must be breaking of this single bond. The electron in the single bond all go to the chlorine. We end up forming a carbon-centered radical. Carbon-centered carbocation, a carbon-centered positive charge. So first step, reading the question and draw out how to form that carbocation intermediate. All right. And what else do we know? The question asks us to explain why are we only forming A and B, but not C? Now, what is this reaction? Again, once we form that carbocation intermediate, what's going to happen next? We have a positive charge. We have a negative charge, OH minus. And obviously, this OH minus can react with that positively charged carbon. All right, so the real question we're trying to answer here is, well, to which carbon this OH minus is going to react with. All right, or if I put my OH minus next to my first structure, well, we can easily say, okay, so the OH minus as a nucleophile attack my carbocation to form my product A. This is an obvious conclusion. What about product B? Why are we forming product B here? Yes?
To form it using resonance?
Right, so we can use resonance, or we can use what we just described. So in here, we have an allylic system. Right, so that carbon, positive charged carbon is right adjacent to that double bond. So using both resonance or our quantum bonding theory, we can write a resonance structure like this. All right, and in this new resonance structure, we can have another OH minus adding to that positive charge or allylic carbocation to form my product B. All right. And last question, why we're not forming product C? Yes?
Is it because the OH would be bonding with a carbon that isn't one of the two terminal carbons within the allylic system?
Right, so that's an observation. But the real reason behind the center carbon not forming a bond with the OH minus, well, in our allylic system, our center carbon doesn't have any positive charge on it. So naturally, when a nucleophile comes interact with that allylic system, it doesn't interact with the center carbon. All right, so that goes back to the shape of our allylic system. So when we draw this allylic system like this, we see that the positive charge are on the terminal carbons of my allylic system. This center carbon does not have any cationic character. Right, and consequently, because the center carbon doesn't have any cationic character, when a nucleophile comes and tries to form a new bond, it will tend to form a bond with one of the terminal carbons. All right, so this is an example of like, you haven't learned anything about this reaction. We will talk about it later on, but by only knowing the nature of these allylic system, you're already being able to predict the product of an organic reaction. And these things are connected to each other. You'll come and see these like stability, resonance stability come and play again and again and again. I just want to use this as a demonstration to show like what is the power of understanding the reaction mechanism? What is the power of understanding chemical bonding in organic chemistry? And we'll apply these to different reactions. But at the end of the day, reactivity and selectivity of organic reactions are all connected by the nature of these chemical bonds. Okay, I hope I didn't confuse too many people, but we'll come back and talk about conformations of alkene this Wednesday.